Hello everyone, I'm Xiao. This is second tutorial of ChemPlasKin. I will show you an example of simulating nitrogen plasma kinetics using external profiles of electric field and electron number density. This example shows how to use ChemPlasKin purely as a plasma kinetic solver. You can find more details of the example from ZDPlasKin website here. We will examine the details of the source code so you will learn how to customize it for your own research topics. Here, I recommend C-Line as an IDE for C++ programming. You can open CMake list file with C-Line. So now we are already in debug mode of C-Line for this test case. The main code is now called test N2 CPP. It's slightly different than the master.cpp file, which is here. Okay. Which is more of a general purpose code, reading parameters from user text files. Here in this nitrogen plasma example, parameters are hard-coded for simplicity. I think this can be a better way to learn ChemPlasKin since the main code will be much shorter and simpler. Plasma reactor.h file has also been customized or simplified. So let's go through the master code. At the beginning, you will include all the necessary header files here, especially this plasma reactor header file. You will use the namespace called Kantara. Before we write the main function, we need to define a few useful functions. Here we have get number density, which convert the mole fraction to number density. So you have input as gas object and the size and the number index of species you want printed out. Let's move into the main function. At the beginning, you will see the definition of log level for ChemPlasKin, which is from CPP bolos, but can also use for ChemPlasKin. We set up time control, the runtime starting with 0, and number of passes. Here we put 10. The bool of thermal effect, we set it true. We want to include thermal effect. Although you will see it be negligible in our test case. Another flag called print reaction rates. This flag decides whether we would like it print the reaction rates, such as this one, see here. Now we need to set up the Boltzmann solver. It print a header and some information. Now we read the data input. This data in is the external profiles of electric field and electron number density. So until here, okay, you finish the reading, and this section is for testing. Okay, you can comment out just to test reading if it's correct or not. Next, we need to set up the species to be configured by CPP bolos, the Boltzmann solver. It's called Boltzmann species. Here we only have nitrogen, and its number density is 1. Sorry, here the not number density, it means mole fraction. Then we need to read the cross-section data, ensure the path to the cross-section data is valid, otherwise give you error. We need to read the collision data, then set up the grid for Boltzmann solver. Here we use quadratic grid, and starting from 1 to 30 electrovolt. This is a grid number, 180. Then we load the collision. Here is log info. It tells you how many targets and being loaded and print out names. Next, we need to set up the gas temperature, reduce electric field, density, and initialize the Boltzmann solver. Here, Ne is initial electron number density. We set up temperature, electric field, Boltzmann species density, and initialize the Boltzmann solver. Now, we should try to solve the EEDF just as a test. This is always a good habit. I recommend you do that before solving the plasma kinetics. So this F0 is EEDF. We give it initial gas from Maxwellian distribution. Then we try to solve this. And then if it's failed, you get error. Now we move to the gas phase and the reactor settings. We build a new solution object from the plasma kinetics, plasma N2 kinetics mechanism files. Again, ensure this path is valid. Here is another information telling you how many Boltzmann processes are there. Then we get the thermal object called gas and define the pressure, which is 1 atm here. Then you can calculate gas density. Next, we need to create a mixture composition. We have nitrogen as a major one. We also have some initial number density of electron and N2 plus used as the seeding. But this will be overwritten by the external profiles, okay? So this setting doesn't matter here. And now we set the state, we input the gas composition into the thermal object and set up temperature and pressure. So here I have a line saying initial number density doesn't matter. Too small value may cause problem. So no matter you use external file or not, you need it's better to have initial number density. So we have initial density. This is just the test lines, not essential ones. Next, we can create the gas plasma reactor object. Okay, this is called ChemPlasReactor. We inject the solution and Boltzmann species. This reactor coming from the plasma reactor class. See, it's from here. And the plasma heat model is defined as default, which means using the detailed calculation instead of the Felitti model. Okay, let's go back. Here is non-thermal. So yeah, if you put thermal effect to yes, it will be no, which means non-thermal is no, means thermal. Okay, a little bit confusing, be careful. Next, we create and initiate an OD integrator. Okay, the integrator we use CVault and initialize it with runtime, which is 0, and the OD object. We can access the kinetic information using this one, solution. It is member class object called kinetics. We can get how many reactions are there. So this vector will hold the forward, reverse, and net reaction rates. Here we have species names, index list. Next, we create the output files, names called output N2 CSV file. We write the headers. We push back the species names. Okay, this is just writing the file's header. Next, we write just for printing out information. So we hold the mole or mass fraction data in this vector, which will be used later. Okay, we can run the simulation now. This is just another log information. This T0 is save the start time, which will be used to determine the execution time of the simulation. Now then we go to the main loop. Before that, we have discharge energy. Its initial discharge energy deposit to the system is 0. Next, we can move to the main loops. We have 2 layers of loop. First is to determine is for the passes number loops. We have 10 passes here. And the second loop is within each pass you have variation of species number density. So you have 2 layers. The dt is determined from the input data as well. And the en, ne, I think this is midpoint interpolation. Format output digit. Okay, this is just some output information. Now we need to update the electric field. Set it up here and check, do we need to update the Boltzmann mixture? If it's yes, we need to update it. Then we update the electric EEDF, reinitialize it. This is very important. Every time you change the mixture fraction and the electric field of Boltzmann solver, you need to reinitialize the solver. Okay, now you update the EEDF. Here, this parameter is a good estimation of delta 0. If you don't know what delta 0 is, you can go to the Boltzmann solver to speed up the Boltzmann convergence, especially for significant varying E over M. Okay, you may just simply use bracket, which will make the Boltzmann solver take the default parameters. Here's another log info telling you the electric field, gas temperature, electron temperature. Now we can update the integrator. Since we use external profiles of electron number density, we need to impose electron number density here. We need to reinitialize the integrator. Next, we can advance one time step forward. Runtime being updated, then we can integrate. After integration, we need to update the solution. Next, printing out some log information. We're going to write in the number density. Okay, here until here. We can check plasma power and energy deposition. So here is a print reaction rates flag. If it's yes, you will print some information like here. You will print all the reaction forward, reverse, and net production. Okay, we finish the loop. We save the end time and print out execution time. This is a full run of ChemPlasKin. Let's check the ChemPlasKin reactor as well. So this is how you build. How do you build the what's unified gas plasma kinetics system? But here we don't have combustion chemistry. We only have plasma kinetics, but they're same. Okay, this is a constructor. We initialize some member variables. This is a thermal object, kinetics. We get the pressure, density. Okay, here just some initialization. Here is number of equations in the ODE system. We have number of species and 4 other parameters. I will talk later. So here is determining which plasma heating model to use. And this function set plasma energy transfer. Let's see it. So this function will remember this one, energy transfer entry in your YAML input. So this function will check the mechanical the file and read this energy transfer entries. Okay, here in the mechanical file, you will see there's no vibrational states of nitrogen. So this map, this evibe N2 map would essentially be 0. Let's go back. Now we'll register energy transfer data for plasma reaction and create a map for all species. Okay, here, E value, evaluation. So this is the most important function in this plasma reactor class, which will be reading by the CVOT and do the time integration. Okay, this is time derivative of solution vector, temperature, enthalpy, plasma energy, a vibration state of N2, and the remaining are the mass fraction of species. Okay, here we see, do we impose external number density profile of electron, and this is DDT. These are the time derivatives. Okay, so here we can determine shall we use constant pressure or constant volume. Now we can get the right hand side of the equation. So here is enthalpy calculation. We move to the energy equation. Here, if it's non-thermal, everything is zero. Okay. If not, we need to calculate enthalpy. Here is the plasma heating model to be used. Okay, this is a fleeting model. This is update Boltzmann mixture. You can update this criteria. If you set a smaller value, it will update the Boltzmann solver more frequently and probably get a more accurate result. But of course, higher computational cost. This is get state, update state. Here are also some useful functions to check the production rates. You can explore them. Okay, now let's try to run the simulation. I can click run. Okay, very quick, just 2.4 seconds. Now let's check the results. Go back here. Example. So this is output results. We can try to plot them. Let's go. Okay, this is species number density as a function of time. I plotted for these 5 species. You can compare it with the ZDPlasKin results. It's here. They are same. Okay, this demonstrates how to use ChemPlasKin purely as a plasma kinetic solver. It can do everything that ZDPlasKin can do. Good, that's for today. Thank you for your attention. I hope you enjoyed. Let's meet next time. Thank you.